Python has had one controversial feature for over 30 years. Some call it a flaw, some call it a design masterpiece. In this video, we're going to finally understand the truth behind the Python GIL and why Python 3.13 changes everything. First, we'll break down what the global interpreter lock actually is and why it was never a bad decision to begin with. Then we'll look at why modern multi-core CPUs turned this elegant solution into a serious bottleneck. After that, we'll explore how Python is removing the lock, including free threading, subinterpreters, and the real meaning of PEP 703. But here's the catch. True parallelism isn't free. We'll talk about the hidden costs, performance trade-offs, and why some workloads may even slow down. And finally, we'll switch perspectives. What interviewers actually expect you to know about the GIL in 2025 and beyond. No memes, no myths, just how Python really works under the hood. Let's start from the beginning.
All right, let's get right into it. If you're a serious Python developer, you've heard about the global interpreter lock, the GIL, and you've definitely heard it's being removed. But the real story here, the one that matters, isn't just about making Python faster. What we're really talking about is a fundamental shift in the language's design, and understanding that is absolutely critical, especially in a technical interview. You've probably seen the memes. You know, the ones that frame the GIL as this simple gotcha for multithreading. Well, yes, but actually no. And look, it's funny, and it gets at a piece of the truth, but it completely misses the why. It misses the entire engineering story. The common wisdom is, well, let's just say it's incomplete. So that really brings us to the core question we need to deconstruct. Was the GIL a fundamental design flaw from day one? Was it just a mistake that held Python back for all these years?
Well, the answer, and this might surprise you, is a hard no. For most of Python's life, the GIL wasn't a bug, it was very much a feature. It was a brilliant pragmatic design choice that actually helped Python succeed in the first place. To really get why it's being removed now, we first have to understand why it was put there to begin with. So yeah, let's reframe this whole thing. For a long time, the GIL wasn't the problem. It was the solution, an elegant solution to a much harder problem that CPython's creators were facing.
Okay, so what is it technically? At its heart, it's pretty simple. The GIL is a mutex, a single global lock. Its only job is to make absolutely sure that only one thread is executing Python bytecode at any given moment inside a single process. That's it. And this is a great way to visualize what's happening under the hood. One thread gets the lock and does some work. And then maybe it waits for I/O, or its time slices up, it drops the lock. Another thread immediately picks it up. They're just taking turns, one at a time. It serializes everything. So, why? Why do this? It all comes down to one critical thing: memory management. CPython uses a system called reference counting. Every object tracks how many things point to it. When that count hits 0, poof, the object is gone. The GL makes this entire process thread safe by default. It prevents two threads from, say, trying to change the same reference count at the exact same time and completely corrupting memory.
And this right here, this is the trade-off. This is the core engineering decision that was made back in the 90s. With the GIL, you got a simple, clean memory model. You got fast, single-threaded performance, which was what mattered for almost everything back then, and, crucially, it made writing C extensions super easy, which is how the whole ecosystem exploded. The alternative, a Python without a GIL, that would have been a nightmare of complexity and probably would have been slower for the most common use cases.
But that elegant solution had a shelf life. As the hardware world changed dramatically, the GIL, which stayed the same, started to become a real bottleneck. It started to create the very problems we're dealing with today. The big change, the inflection point in this whole story, was the rise of multi-core processors. All of a sudden, the hardware could do true parallel processing. But CPython, because of the GIL, couldn't use it. For any task that was heavy on the CPU, you could have a 64-core machine, but your Python process was only ever going to use one of them at a time.
And this wasn't some abstract issue. The people really feeling the pain are in fields like scientific computing, AI and machine learning, and large-scale data processing. The very domains where Python is now completely dominant. The GL forced everyone into complex workarounds, like using multiprocessing, which comes with its own baggage and overhead.
And hey, you don't have to take my word for it. The official proposal to remove the GIL, that's PEP 703, says it right there. The workarounds are complex to maintain and hurt developer productivity.
The once elegant solution had officially become a very expensive problem.
Which brings us to today, and the absolutely monumental engineering effort to finally make the GIL optional. And let me tell you, this is so much more than just deleting a few lines of code.
Okay, first things first, and this is a really important detail. The GIL isn't just gone. It's optional. You now have to compile a special free-threaded version of Python by adding a flag, -disable GIL. This is huge for backward compatibility with the entire existing Python world.
So instead of that one big lock, the new system uses what are called thread states. A thread has to be in the attached state before it can touch any Python objects. But, and this is the whole point, now multiple threads can be in that attached state at the exact same time. That's the key that unlocks true parallelism.
Okay, let's look under the hood, because this is where the real work happened. To make any of this possible, the core of the interpreter had to be completely re-architected. That simple reference counting, it's been replaced by much more complex systems. There's a whole new stop-the-world garbage collector that has to pause everything to clean up memory safely, and fundamental things like lists and dictionaries had to be rebuilt from the ground up to be thread-safe using much more fine-grained locks.
Now, this re-architecture is an incredible feat of engineering, but it is not free. There is a cost, and we have to talk about the real trade-offs that every single Python developer needs to understand.
And here it is, the #1 trade-off you have to understand. All of that new machinery for thread safety, the new reference counting, the fine-grained locks, it all adds overhead. Right now, the estimate is that it slows down normal, single-threaded code by around 9%. There is no such thing as a free lunch in software engineering.
The other massive cost isn't in performance, it's in the ecosystem. Think about it. Thousands of C extensions, the things that power libraries like NumPy and Pandas, were all built assuming the GIL was there to protect them. Every single one now needs to be checked, and likely updated, to be safe in this new free-threaded world. This is going to be a slow, multi-year process.
And if you want to understand just how high stakes this change is, just read this quote from the Python Steering Council. They are saying, point blank, that if this whole thing proves to be too disruptive for the ecosystem, they have the option to roll back the entire project. That's how carefully they're approaching this.
Okay, so let's tie all of this together. Why does this level of detail actually matter? Because when you're in an interview and someone asks about the GL, they're not looking for the meme. They're testing your understanding of deep engineering trade-offs. This is it, the classic design question. And it's not a trivia question with a right or wrong answer. A junior developer might just say, no, the GIL is bad. A senior engineer will give a much more thoughtful answer.
So here's your playbook for a senior-level answer. 1, you start with the history. Acknowledge that the GIL was a smart choice that simplified everything and made single-threaded code fast. 2, you connect it to the technical reason, making reference counting thread-safe. 3, you articulate the trade-offs, simplicity versus parallelism, and explain why that balance is shifted over time. And finally, you propose a modern alternative. You show your thinking about design by saying something like, well, today we might have started with a more advanced garbage collector instead of reference counting. That's the answer that shows real engineering maturity.
And I'll leave you with this final thought. For decades, the GIL, for all its faults, protected Python developers from the absolute worst kinds of concurrency bugs, like data races. Now that the lock is optional, Python is more powerful, yes, but it's also more dangerous. The next big chapter for the entire Python community is going to be learning how to master the very class of problems that the GIL so elegantly solved for us all those years ago.
That wraps up all section. Smash that like button, subscribe for more content like this, and drop a comment below. See you in the next one.